Welcome back. In this lecture number 2, we are focusing on ROI for energy projects, particularly renewable energy systems. We will break down how to calculate returns, account for system performance, and factor in incentives so your numbers are realistic and persuasive. By the end of today, you will be able to build a professional ROI model that works in the real world, not just in theory. Here, what we will cover today. First, we will go over ROI calculation and we will cover its method, specifically for renewable energy. Next, we will learn to model PV systems. That means understanding capacity factor, and energy yield. We will integrate incentives like tax credits and feed-in tariffs, and we will see how net metering changes the savings picture. Finally, we will put all of this into a complete PV ROI model in Excel. By the time we wrap up, you will be confident about tracking solar projects evaluation from start to finish. Energy projects, especially solar, require big upfront investments. ROI analysis helps us make sure these projects are financially capable. It's not just about the direct cost saving. It is about capturing indirect benefits like reducing carbon emissions and many other environmental returns. ROI also lets us compare different technologies side by side and choose the best fit for our needs. Let's start with the basics. A photovoltaic or a PV is a system that converts the sunlight into electricity. The system's capacity, usually in kilowatt peak or kW small p, lowercase p, is its maximum output under the ideal test conditions. Okay, but in the real world, actual outputs depends on the capacity factor, on the clearance of the sky, on the weather, on the cleanness of the panels, which reflects also depends also on the location and about the age of the equipment in general. And we call it efficiency of devices. Annual generation is simply capacity multiplied by the capacity factor and then by the number of hours in a year. Roughly speaking, we consider this amount of hours, which is 8,760 hours. The capacity factor is the ratio of what your system actually produces to what it could produce if it ran at full power. This varies. For example, sunnier location, like in Dubai, in Jordan, have higher factors. Cloudy areas, like in London, it could lower. So most systems fall between 15 and 25%. And it's about the experts' decision to choose between these percentages, between 15 or 25%. Okay, so short example, let's take a system that its peak energy generation is 100 kilowatt peak. System at a 20% capacity factor produces 175,200 kilowatt hours per year. Okay, so the calculation, I think it's simple as straightforward. Incentives can make or break your ROI. So tax credits lower your tax bill based on project cost. Grants are direct funding from government or agencies. Feed-in tariffs pay you a fixed amount for every kilowatt hour you send to the grid. Net metering gives you credits for excess electricity that you generate and feed up into the grid. And carbon credits can be sold for additional revenue if your project reduces emissions. Many corporates, they are interested in obtaining what we call it the RECs, REC, which is renewable energy certificates in the United States, and the GOES is guarantee of origins that use it in Europe, and also the IRECs for any countries beyond the North America and Europe, for any countries that they do not have a certification procedure for declaring carbon mitigation efforts. So for each 1 megawatt, they get a one certificate. This is very important for many of the corporates to ensure its integrity to the public and transparency and accountability to their commitment, such as Amazon. When they have declared the pledge, they are committed to reduce carbon emission by zero carbon emission by 2040. So in order to ensure for the public that they are transparent and they are accountable for their commitment, they use these certificates as a declaration, mostly in many other types of commitment, like what we call it the VPPA, virtual power purchase agreements. We will talk about this later in a different lectures. So net metering lets you offset your power bills with your own generation. So if you produce more than you consume, the extra goes to the grid and you get credited. Sometimes at a retail rate, sometimes at a wholesale. It depends on your market or grid operator. So in some countries, the market and the grid operator differ. In many other countries, in the AMAT region, the Middle East, Turkey, and the Gulf area, the operator and the market market operator for the grid is the same. When calculating the ROI, we have to factor in these credits, or we will underestimate the project's value. So to start building a PV ROI model, we first define our inputs. So we need to have these inputs clearly defined and clear to accuracy as much as we can. So we will have the capex of 150,000. That's the capital cost, or what they call it the upfront cost, $150,000. And we will take the properties from the manufacturer about the system that will produce 100 kilowatt at its peak time, 20% capacity factor, which is mostly, as I just mentioned, it could be ranging between 15 to 20%. The price of kilowatt, it's 12 cents per kilowatt of electricity consumed, 2,000 annual saving of operational expenditure, 25-year lifespan, 5% discount rate, plus a 20,000 grant from the government, could be, or the local municipality, and a feed-in tariff of 5 cents per each kilowatt per hour. So let's go and do this calculation. So step number 2, after defining all these important requirements, we have the annual output is easy to calculate. The capacity times capacity factor times 8,760 hours. These are the hours that the total amount of hours throughout the year. So some of you will ask me, but the sun won't operate all the day long. So that's why we have the capacity factor. We multiply the whole rate, the whole accumulative summation with 0.2, or 0.15. That's already been calculated because it depends on the location. So depend on the also the number of Sundays in Jordan is completely different than the number of Sundays in London. So in London, we will increase the capacity factor by 0.2 or 0.23. But in Jordan or in Dubai or in any other country, we will reduce it to 0.17 to 0.2. Depends also in the situation, because in a hot climate area, the system perform less. So for example, in Jordan, the system perform well in comparison to the Jordan Valley. So the Jordan Valley, we will get it a higher percentage, we'll put it 0.22. But in Amman, which is more moderate climate, we will put it 0.17 or 0.15. All right. So this is a clear explanation for your future understanding. So we then separate the value from the self-consumption and the value from exported electricity under the FIT rate. This gives you the annual gross revenue from the system. Annual net savings are your self-consumption savings plus your FIT income minus your OPEX. In our example, that's the $12,000 from self-consumption plus $3,760 from FIT income minus the $2,000 in OPEX, which equals to $13,760 per year. Now let's jump to the payback period. Payback is simply the adjusted capex after incentives divided by the annual net savings. Here, that's a $150,000 minus $20,000 divided by 13,760, which comes out as about 9.46 years, which is roughly acceptable. Like you're getting back your investment by 10 years, which is moderate. For NPV, we use Excel's NPV function with the 5% discount rate and 25 years of net saving, then subtract the net capex incentives. A positive NPV means the project is financially viable, as we have discussed that in the previous lecture. The higher it is, the stronger the case, which is important for investors and decision makers to see this NPV number. To get the IRR, we get the initial investment as a negative in year 0 and the net savings as positive for each year. If the IRR is greater than the discount rate, the project returns are considered attractive. Solar panels lose efficiency over time, usually about 0.5% to 1% per each year of operation. We account for this by multiplying the first year's output by 1 minus the degradation rate for each subsequent year. This makes our projections more realistic for long-term planning, and that's what's differentiated between the simple payback period and the more realistic one. We use sensitivity analysis to test how the ROI changes with different conditions, like higher or lower electricity prices and other factors. This helps us to observe the project's risk profile and prepare for changes. Keep your inputs, calculations, and outputs in a separate sections for clarity. This is one of the most important tips when you are dealing with such building a financial model for a sustainable project. So use named ranges that you can change inputs quickly. Add scenario toggles for comparing different assumptions, and use charts to visualize cash flow, payback, and cumulative savings. So for graphics, charts can make your model far more persuasive. Show a cash flow chart over the project's life, highlighting the payback point, plot the NPV growth over time, and compare scenarios side by side. This could be all done by Excel. So let's avoid the common mistakes and pitfalls that most of beginners fall into. So watch out for these. Ignoring the degradation, overestimating capacity factor, and forgetting the OPEX can rise, and ignoring these factors could result with unrealistic estimates. So any of these can make your model overly optimistic, and this is what we need to avoid. So this is your practice exercise. Now you have this challenge. You need to model your ROI for a 250 kilowatt peak system with 400,000 capex, $50,000 incentives, 18% electricity capacity factor, and the price is 15 cents per each kilowatt per hour. Don't forget the degradation factor and the fit income. So I hope you will sort this out clearly. So before we end up this session, the ROI of PV projects depends on accurate yield estimation. So careful inclusion of incentives and net metering and realistic readings are very important to ensure the accuracy of the model. With the right Excel setup, you can make these models dynamic, scenario-based, and highly reliable for decision making. Thank you very much for listening to this lecture. This is Dr. Zaid Ziadat from Jordan. I wish you all the best. I'll see you in lecture 3 for an advanced information regarding sustainability financial modeling. Thank you and see you later.